It should be okay. So good morning, everyone, and welcome to this class in the topic of power electronics in electric vehicles. My name is Wilmar Martinez, and I will be talking a little bit about electric vehicles and myself in a minute. This one, yes. But before that, I would like to check with you as a warm-up. Please follow the link or please follow the QR, because we have some couple of questions there that we will use during the session today. So yeah, if you're already there, I will just switch, and then you can use this code. I think you can already start, right? Can you confirm that you can already answer this question? I will check myself. See if I can. Did you get the chance to go to the poll? I will open it again here. I will activate it. So yeah, please answer. In your opinion, what are the challenges in the adoption of electric vehicles? And personally, why wouldn't you buy an electric car? Yep, charging speed. Cost. So charging is the main one. Emissions, CO2, integration. I suppose that the street is charging on the street. The production of electric vehicles, infrastructure, battery technology, recycling, integration. Yeah, but yeah, it's quite interesting that you put charging prices as the main one. Of course, the grid and batteries. Yeah, because we will be talking a little bit about that. So I will stop it here. But quite nice to see this interaction. So let me get back to the slides. So a little bit about myself. I think that most of you don't know me. I'm Wilmar Martinez. I'm originally, I think I will move this one, yes. Originally from South America, from Colombia. Did my master's there. Then I moved to Japan to do my PhD and work also in Japan in electric cars, actually with Toyota, and doing hybrid cars at that time, or the development of the third generation of the Toyota Prius. I did a postdoc in Finland, also worked in ETH Zurich, and since 2018, I joined KU Leuven as a professor. Also, I am a research line coordinator in Energyville, and that's why we are using actually the Energyville template for this session, coordinating the activities of power electronics there, along with Johan Driesen as well. I teach, of course, and I teach several courses: electric vehicles, power electronics, electric drives, machines, mostly for the industrial engineer side, helping Campus Diepenbeck, Campus Hill, and also Leuven. Yeah, I have participated in many publications, patents, and some book chapters. So that's me, and that's why I was invited to give these two sessions about electric vehicles, and I hope we can learn a little bit about those. I work in Energyville. I always use this nice representation of how we went from a coal mining facility in Henk in the Waterschei area to an institute dedicated towards sustainable energy. And for me, that's a quite nice representation of what energy transition is. I think many of you have been in Energyville. For those who have not been there, this is how the campus look like. We have two buildings. This is Energyville 1 and this is Energyville 2. And there we have collaborations of 4 institutes, mainly KU Leuven, University of Hasselt, Vito, and IMEC. We have several activities, so we do research, basic and applied research. We try to be in the whole value chain, going from materials, components, systems, circuits, until even markets. And we have that value chain in Energyville. We assist also in the development of human capital. And we also give input to, for instance, policy making in the region of Flanders, Belgium, and also in Europe. We are more or less 500 people, 400 researchers, 8 research lines. And here is where I would like to do a little bit of zoom there, because we have these 8 research lines. During this course, you will actually see a lot of, for instance, the research line, where is it? Solar, a little bit of batteries, of course, electrical networks, and power electronics. And that's the research line where I belong to. We have within the power electronics research line, we have 3 different roadmaps. The first one is power converters, so fully into hardware. So we do hardware, and we develop, test, build that hardware. We also do low voltage DC grids, and those are mainly the activities of Johan Driesen. I'm sure he already mentioned that to you. And we also do reliability of these components, both at the system level and also at the converter level. And today's session, and also in the next week, we will be talking a lot about this roadmap, which is the converters roadmap. There we work fully into applications, and I will mention which type of applications we work for. Topologies, converter topologies, and there we have 3 main USPs, unique selling propositions in our group, and it's basically the study of passive components. You will see a lot of passive components today. Wide bandgap semiconductors, so new semiconductors like silicon carbide or gallium nitride. Belgium is actually quite important in the topic of gallium nitride nowadays, and also design automation, new techniques to design power converters in a better way. So those are, in a nutshell, what the 3 main roadmaps and our uniqueness, so to say. If we do a little bit of zooming each of the roadmaps, like the power converters technology, we try to design, test, build converters for the so-called combined performance. So we don't only focus on one of these, like efficiency, power density, gain, cost, CO2 footprint, for instance, but we combine those and we design converters based on those characteristics. As I mentioned, we put emphasis on wide bandgap devices and magnetic components, and we do that also from the point of view of models, so multi-domain, multi-layer, multi-physics models, and with that we build the value chain of the converter technology. Low voltage DC grids, I'm sure Johan already mentioned this part. In Energyville, we have an installation of a low voltage DC grid, bipolar. We call it also a nanogrid in the building, and actually we are interconnecting buildings in DC. So DC is quite important. And yeah, we are doing power flow monitoring measurements. We are testing solid state breakers, because in DC that's not easy, and power converter testing, and we can interconnect it with other labs. And the last roadmap is towards reliability. So we are building mission profiles of components and systems, and we are doing accelerated lifetime testing, gating data to evaluate those components. at the end to do condition monitoring, to predict maintenance via sensors, via a better design of topologies, and also control. So yeah, those are the three main activities in our group, in the power electronics research line, so to say. And then the applications, and that how or why I mentioned in this specific class is because we work a lot in battery chargers, so onboard chargers, off-board chargers, and also wireless charging. And today I will be talking a lot about onboard chargers and DC chargers, and that's quite important because, as you said, one of the challenges is actually charging of electric vehicles, how that affects, for instance, batteries, and what could be actually the effect towards the grid. And if you see, those were the main three words out of the poll at the beginning. We don't only work for electric cars, we also work for networks. We do power converters for low voltage DC grids and also for high voltage DC grids, among other applications, like for instance, aerospace, consumer electronics, hydrogen production, electrolyzers, not only for hydrogen, also for CO, CO2, ammonia, and so on. Good. I will bring to you two main projects that we are working on at this moment, and I think they are relevant for this class. The first one is the Power Drive project. Is a Horizon Europe funded project in the topic of electric vehicles. It's actually the name is Next Generation Electric Vehicle Power Electronic Developments or Component, funded by the European Commission. And here you can see how we split the work, and we put quite a lot of work in the onboard charger. I myself, I am coordinating this project, and we are working in the onboard charger. And there you can see some keywords like transformers, batteries, gallium nitride and silicon carbide semiconductors, bus bars, cooling technology, and so on. And those are keywords that we will explain in the coming slides. This is a project where we are trying to innovate for 800-volt battery packs in cars, and with the purpose of integration. So we are integrating, for instance, inverters on motors in the same case. And we are also trying to integrate onboard chargers on batteries. So if you see here the keyword integration here as well. And not only looking into technologies, power electronic technologies, but also doing modeling, and also looking, for instance, into the effect of humans and traffic in the powertrain, which is, in my opinion, not that much explored at the moment. So yeah, this is the part of powertrain. And remember that word powertrain, because in a minute we will be talking about that. We have 10 partners in whole Europe, and actually Volvo, the Volvo group is the car manufacturer, so to say. In the project, we have some other big names, like for instance Infineon or SMA or Rogers in Belgium, doing technologies, and also some other universities doing developments. So that's the first project that I will be talking about today with regard to powertrains. And the second project is, although it's here, it says 6 because we have a certain number of projects, but these two are the relevance for this course, is more towards the topic of charging architectures or charging infrastructure. So powertrain on one side, electric vehicle charging infrastructure in the other side. And here, for instance, we have this project also together with Johan Driessen, funded by FOD Economy, so by the Flemish government. And there we are doing design and performance of evaluation of charging infrastructure. There, for instance, we are looking inside the car. We are looking into different cars, like you can see here, a wide range of electric cars. And we are looking also into the chargers, so charging technology. And we are looking, for instance, into real solar generation. For instance, in Energy Bill, we have more than 300 kilowatt of installed power in PV, and there we are taking that information to help us design charging infrastructure. For instance, what type of voltages should be used here? What type of converters should be used in this part? Should we use DC, for instance? And if we use DC, is it monopolar or is bipolar? And if we use AC, where we put the converters, for instance, if we have many charging points, meaning that we will charge many cars, where we put the converters and what type of converters. So all of those questions are answered in this project. And yeah, and I will be talking about more about charging infrastructure next week. Yeah, so with that, I would like to do the transition towards more the topic of electronics in electric vehicles. So doing or making a zoom there. So going really from the topic of the research line of power electronics, the type of roadmaps that we have, then the topic of electric vehicles, and there where do we work in electric vehicles. This is well known by you. I know that many of you have attended already the electromobility course of Johan, so you know it very well. But just to make a quick summary of where do we have electronics in electric vehicles, I always divide the electronics behind the battery and after the battery. So behind the battery, we have, of course, the charger, whether if it's an onboard charger or a DC charger. We have this type of electronics, like for instance, if we have a DC charger, usually we have, sometimes depending on the battery pack, we could have a converter there to step up voltages or to reduce voltages, depending if we have, for instance, an interconnection to a medium voltage DC line, then we need a converter to step down the voltage. And the conventional one that we will talk a lot today is, for instance, the onboard charger, where we have basically the AC grid, and then we have an AC to DC conversion, and then a DC to DC conversion there. And yeah, the battery in between. Then after the battery, we have also two main loads. One is the electric motor, and the other one are auxiliary systems. The electric motor being the largest load there in terms of power, and there we usually have an inverter, and also we have, depending on the voltage of the motor, we can have also a DC-DC converter. Like for instance, I mentioned that I was working a lot in Toyota, and we always work with the case of the Toyota Prius. And the Toyota Prius, we have a rather low voltage battery in the range of 200 something, depending on the model, 300 volts, and electric motor we have one of 650 volts. So there, of course, we needed a converter to step up the voltage towards the 650 volts needed by the motor. Today, in battery electric vehicles, most of the time we try to have the same voltage in the battery as in the motor, like for instance 400 or 800 volts, so that we can skip this conversion step, and then we go directly from the battery to the inverter and then to the motor. So yeah, those are basically the two parts: the charger and the powertrain or the car, so to say, or the system to power the electric motor. But yeah, everything starts with the battery in between, or the storage system. It's not always a battery. Sometimes we have supercapacitors or ultra capacitors. That's also important to be mentioned. So let's start then talking about batteries. So how the charging process is done before we dive into battery chargers. So we know that most of the, if not all the electric vehicles today, they use lithium-ion batteries. In the past, nickel metal hydride was also used, and several decades ago, even more than 100 years ago, when the electric vehicles were invented, we were using lead-acid batteries. So lead-acid, nickel metal hydride, and today we are having different types of lithium ion. But all of them, or if not most of them, they have this skateboard approach where we have this big flat battery pack. And if we look inside that battery pack, basically we are having battery cells, which whose voltage could vary a little bit from depending on the technology. But at least for this exercise, we assume that those are low voltage cells. They also have a specific volumetric energy density or gravimetric energy density. This is just for reference. Of course, there are, depending on the technology, we could have different values. So that's 450 watt hours per liter or 256 watt hour per kilogram. Those are just for one specific technology, but more or less lithium ion technology moves in those ranges. What is important, at least for this case, is that if we have, for instance, a larger battery pack, meaning more cells, of course, we will run the car in a longer distance, or we will have a larger range, so to say. So that's pretty straightforward. There are many ways to charge these batteries. The most well-known today is the so-called constant current, constant voltage. This is quite important to introduce the next part, so really bear with me in this part. So constant current, constant voltage, so we can identify basically two segments between T0 to T1 and between T1 to T2. So T0 to T1 is basically constant current, so quite straightforward. So we have a constant current voltage, more or less, in most of the cases is more or less constant as well. Of course, if we have a deep discharge, voltage increase is a little bit at the beginning, but then more or less keeps constant. And if you do the power of these two, meaning that we have voltage and current and then we have power, more or less we can see that the power in between T0 and T1 is more or less constant. But after T1 is the part of constant voltage, so you can assume that of course the voltage will be constant, and current actually starts to decrease. And if you do the power once again between these two, you will realize that we have constant power until T1, and then the power decreases. And that's why actually, if you have seen in your phones that the phone charges quite fast until more or less 80% of the state of charge, but after that it's really, really slow, and it's because of this. Why we do that is basically to protect the battery, and we have the so-called battery management system that tells the charger really to limit the power to this part. And this is quite important, as I will be mentioning in a minute. Usually this T1 is 80%, depends pretty much on the chemistry of your battery, and the lifetime, and many other factors, temperature, humidity, and so on, but it's more or less around 80%. So if you think into this approach, if we have a larger current here or a higher current here, that means that we will be shortening that time, and that's the concept basically of fast charging. In order to have a fast charging, we need basically higher current, so quite straightforward as well. And I'm mentioning this is quite important because when we look into charging profiles of batteries, this is quite important. And here, for instance, we have some real examples. This is an Audi e-tron, and here we are charging, for instance, around 150 kilowatts. And then you can see that more or less until 80%, we have a constant power. And then after 80%, it starts decreasing. And here we have some other cases like a Jaguar I-Pace, a Kia Niro, a Hyundai Kona. So more or less all of those, they go constant until certain time, and they are after that they start decreasing. And here you can see that some of those is actually below 80%. And here is actually this particular case of a Tesla Model S. The next slide is fully into this one, just to check that it's not constant at all. This is exactly, I will explain this in a minute, but here is basically the message is that battery chargers do not work at peak power. That's a myth or something that we sometimes tend to think that if I have a battery pack of 100 kilowatt hours and then I have a charger on the street or near my place, and that charger is, for instance, or a 50 kilowatt charger. So if I have 100 kilowatt hour, 50 kilowatt, we tend to think, okay, I just need 2 hours to do a full charge if I am really in a low state of charge. But that never happens. Why? Because of this, because we probably will start charging at 100, at 50 kilowatt, and after sometimes it starts decreasing because of the battery management system. So it's never 2 hours, it's actually way longer. And I mentioned that I wanted to talk a little bit about this Tesla Model S. So this is the real information. It's a rather old Tesla. So depending on the lifetime of your battery, your charging profile changes. So there you can see that it rises quite quickly until 93 kilowatts of power. This is power versus a state of charge. And then it starts actually decreasing. Why? Because as you know, this is done at really high current. And we know the Joule effect issue, that if we have higher currents, of course, we are producing way more losses, I square R. So we are actually heating up the battery, and in order to prevent that the battery goes to let's say, a thermal runout problem, we limit actually the current. So we start decreasing the current until points of, for instance, 30% of the maximum rated power. So yeah, this is a Tesla Model S. Again, the message is that we never do charging at constant power, and this part of efficiency, I will explain it in the next two slides. The charging speed depends really on different factors: temperature, state of charge, the lifetime of the cell age, and also previous, for instance, fast charging cycles. Like for instance, today, I have seen this when I try to charge my car many times with the fast chargers. After, for instance, 1 week of charging almost every day, I have these messages like the maximum power is actually limited, in order to prevent damages to the battery. That's quite preventive, because there are already some studies that they mention that fast charging is actually not that harmful as we thought, and so that we can do more fast charging more often, so to say. But yeah, that's a topic for a quite deep discussion in this DC charging. I will talk then about this topic of efficiency. So why this part of charging profiles is quite important for battery charging, and is because of the fact of efficiency in this case. So how we do those chargers, we have two options. We do it onboard or offboard, and usually the onboard chargers, they have rated powers between 3.6 until 43 kilowatts. Most of the chargers today in many cars, they are 11 kilowatt chargers, three-phase, or 6.6 kilowatt single phase, for instance, in the US. And there, the concept of off-board chargers, and those are basically modular. At the end of this presentation today, I will explain this more in detail. And their power per module changes. So we can have power per module between 10 to 33 kilowatts for small chargers. For more premium and high power chargers, we can have more modules. And even today, to charge, for instance, heavy duty vehicles, like we have this concept of the MCS, the megawatt charging system, that's done with many more modules. What changes is actually the power per module, as you can see here. So different target powers, different number of modules and power per module. And for instance, for different powers, we could have, for instance, 50 kilowatts, 350, 1 megawatt, and so on. A different modular design is required. But let's do a zoom in one of these modules, and let's look actually what happens when we have, for instance, one of these profiles as this Tesla Model S. So inside, and we will look in detail about the electronics inside these chargers. We usually have, if it's an onboard charger, we have an AC to DC and then DC to DC blocks. And if it is a DC charger, we have only DC to DC. And this is a classic example of a DC to DC converter. It's a dual active bridge converter, quite simple in its schematic. So we have a full bridge in the primary, a full bridge in the secondary, and a transformer in between. And yeah, that's why we call it bridges there. And a dual active bridge is called because basically we have certain difference in between the phases of the primary and the secondary. And with that synchronization of those phases, we have the concept of a dual active bridge. So the ones that had already attended courses of power electronics, you know it very well. This is more or less the voltage ratio between the primary and the secondary. So we have basically V2 over V1. So the output voltage over the input voltage, and also with basically the ratio of the turn ratio in the transformer. And this is a classic output power, let's say, waveform, or let's say configuration in the dual active bridge. So we have the phase shift modulation. Here we have basically the phase shift. So the phase shift between the primary and the secondary. So we can have different angles there of phase shift. And we have also the output power per unit. Let's say we want a constant power. Basically, we want an output power of 1. But here the point is that depending on this voltage gain here, this equation D, depending also on the phase shift between the two bridges, we can have all of these configurations, all of these lines. You can see it here, voltage gain of 0.5, 1, 1.5, 2, 2.5, and so on and so on. And the thing is that this converter, power electronics converter, has only really high efficiency in these white zones, the so-called soft switching zones. If our converter works out of that white zone, meaning these red zones here, is the non-soft switching zones, and there we have a big problem of losses. So losses really go high. We have also problems of EMI, electromagnetic interference, and so on and so on. The thing is, if we have this charging profile, as I mentioned at the beginning, the type of the Tesla that has all of these points, basically our converter will be working like this. Every time that we move in the charging profile, we will end up in this really not high efficient zones, and that's a problem for many things. We are actually wasting a lot of energy, and as we will see later in the presentation, and we are actually also having reliability issues in the semiconductors, in these capacitors, because we are having the concept of hard switching, or basically non-soft switching in this converter. We need larger filters, so yeah, quite many problems for this. And this is the reality. That's what happens today when we are actually charging this type of profiles. The chargers are basically single piece of hardware, while we have many types of cars outside to charge. So that's one of the issues. Good. So yeah, that's basically the introduction of this segment of this class, and it's basically battery charging, how charging is conducted, why efficiency is important, and why the electronics inside these chargers, either if it's AC or DC chargers, even if it's a wireless power transfer, a wireless charger is exactly the same. We have the same issues of efficiency, and with those, we will move up to the next part. So these two sessions, as I mentioned, will be divided basically in two segments. One being the powertrain and this keyword, and the other one being charging infrastructure. And that's quite interesting because last week and 2 weeks ago, actually, together with Johan, we were in California attending this APEC conference. It's Applied Power Electronics Conference and Expo. Is the largest power electronics conference worldwide. Actually, more than 6,000 people attended there. And there we have one of these rap sessions because it's a quick session, is not because it's a rap music. We wish. And there we have one of those was actually this charging infrastructure expansion versus powertrain technology advancement, which should be prioritized for electric vehicle adoption. I started the class making this poll of what are those challenges in electric vehicle adoption. And now I would like to hear from you. What do you think about this question? Charging infrastructure expansion or powertrain technology advancement? I already mentioned that we have many things to work actually inside the car. We know that we have many challenges also with regards to infrastructure. You mentioned it there, how to charge those cars. Yeah, I would like to hear from you. So please join once again the poll about charging infrastructure expansion versus powertrain technology advancement. So yeah, this was the first one. So thanks for that. And then the second one, please vote. Yeah, I think. Yeah. I think we can give some 30 seconds to this one. Here we have a 4-1 more into charging infrastructure expansion. Let's give it another 10 seconds. Okay, we have more powertrain enthusiasts. That's good. This is quite relevant. As I mentioned, this was actually a forum, a full forum with more than, I cannot mention, but hundreds of people in that forum really answering this question. So this is really relevant at this very moment to see where we put the efforts really when we want to have these targets met, like zero emission transportation by certain time. How are we gonna do that? And yeah, I would say most of same in that forum, most of the people were actually putting more efforts or thinking that we should put more efforts in charging infrastructure. But I would like to hear from you. Why did you vote for any of these two? So yeah, why? Please explain. Put some keywords there. Why do you think charging infrastructure is more important, or why do you think powertrain technology is more important? I think we can give it 1 minute to this one. Hmm? Also, of course, if you have any question, just interrupt me. And also, if you have any comment, yeah, please just open your mic and we can discuss it in detail. Yeah, cost. Legislation. Yeah, legislation is also quite burden, big important burden there. Bottleneck. Yeah. Yeah. Charging infrastructure is less developed than electric cars. Let's say technology is of course there. It has been already actually before the development of modern electric vehicles. But yeah, it's not as fast as the development of electric cars, of course. Yeah, let's give it another 15 seconds if you have something to write. Efficiency, yeah. Okay, so let's close it here, and then we can dive directly into yeah, battery charging in detail. Good. So that was basically the introduction of this part. Now I will be talking a lot of the two main battery technology charging, so to say. So onboard chargers and offboard chargers. And there I would like to acknowledge one of our researchers, Hans Wouters, that he has been working a lot in these onboard charging technologies, as we will see in the next slides. So once again, the same slide that I presented at the very beginning. In my opinion, there are basically four types or four technologies to charge a battery nowadays in a car. One is the AC charging onboard charger. We call this most of the time AC charging, but it's actually not fully correct. It's better to call it onboard charging because we can do also, let's say, high power charging also with AC. That's also possible, but we don't use it most of the time because for high power charging we call it also DC charging, and there we have these distinctions. But it's better to call it onboard and offboard. That's more accurate in the sense. We can also have DC charging using onboard hardware, and that's also possible. So better onboard and offboard charging, and there we can distinguish many things. DC charging or offboard charging is also referred to fast charging, and there you can see actually many terminologies like fast charger, ultra fast charger, flash charger. There are quite many. So where we put the boundary to call something flash or fast or ultra fast or super fast, there is no real understanding of that. And the third one is wireless charging, is still not as developed as the other two, but also promising in many areas. We will not talk about that in this class, but it's also important in the technology division. And there is a fourth one that I don't include here, and it's basically the concept of battery swapping. Here in Asia, where I am right now, actually, that is used a lot for motorbikes, for small scooters or mopeds. That's used, and that is a business model is let's say exists. To some extent, it works, but we are not thinking in battery swapping, at least in electric cars and in passenger cars. Not even, for instance, for heavy duty. So yeah, that's why we will focus only on these two, and this part is regarding the onboard charger. So this is basically how this is how onboard chargers look like. So these are the segments there. So an onboard charger here in this lines is composed of basically three things. The first one is the filters. We have an EMI filter. Then we have the rectifier, so AC to DC conversion, and then we have the DC to DC conversion isolated one. So those three main blocks make an onboard charger. And I already mentioned this could be powered by a single phase or a three-phase installation. So yeah, that's the onboard charger. The onboard charger is connected directly to the high voltage battery, either 200, 400, 800 volt battery. And even today we are discussing the concept of 1200 volt battery packs. That battery is actually connected to an inverter and then directly to the motor. And also we have low voltage batteries that are basically the ones who power low voltage loads, like for instance the radio, the air conditioning, all the computer inside the car. All of those are actually powered by this low voltage battery. And then we have a DC-DC converter also to charge that battery. And we have the concept of the fast charger, the DC fast charger or onboard charger, once again, which is basically connected directly to the battery. So we bypass actually this onboard charger in order to connect it to the battery. When we talk about onboard chargers, it's important to talk nowadays. Yeah, this is actually a real photo. If you ever visit us in EnergyVille, you will see actually these chargers there. This is a charger used for an Audi e-tron, and a quite similar one is used actually for the Porsche Taycan. The Porsche Taycan being an 800 volt car, and the Audi e-tron being a 400 volt car. And yeah, maybe a fun fact, most of the Audi e-trons that are being sold in Europe are actually produced in Belgium, in Zaventem. So that's quite interesting. But yeah, I will be talking a lot about this guy here. I was mentioning that if you visit EnergyVille, you will see a lot of this because we are doing quite many analysis on these onboard chargers. I was mentioning that when we are talking about onboard chargers today, we need to talk also about the concept of bidirectionality, meaning that it's not only taking energy from the grid to charge the battery, but it's also taking energy from the battery to charge the grid. And that's why we call that there is actually more than just a charger. So yeah, we can power our homes, we can power our loads, we can even sell electricity back to the grid. We can do it that in a cheaper way. We can be more green to some extent, and it should be, of course, in a secure way. And that's the concept of vehicle to X. So I'm sure you have seen this a lot. The concept of vehicle to grid, vehicle to home, vehicle to vehicle, vehicle to load, and it's basically using the battery to power our houses. And here is a little bit of homework for you, or even you can type it in the chat, or you just open the mic. Do you know how much energy do you use per month or per day in your house, in your apartment, in your dorm? Yeah, how many kilowatt hours do you consume per month or per day or per week or per year? Do you know that number? And if you do it, just type it in the chat. Yeah, so we have Tiago saying 4,000 kilowatt hours per year. That's more or less, if we do a rough calculation, a little bit more than 10 kilowatt hours per day, more or less. 11, 12 to be more exact. 800 kilowatt hour per month. Yeah, and so you can refer it more or less to that number. If you don't know that number, I really invite you to go and check the energy bill, the consumption of your house. Also to check, for instance, the cost of kilowatt hour that you are paying or that your family is paying, because that's also quite important to know how, for instance, how efficient we are, how much energy we consume. It's quite a challenge because we talk, even myself, we talk always, yeah, we need to be green, we need to be more energy efficient, and sometimes we don't even know what is our own consumption. We don't know actually our own efficiency. That's something that many people don't know. But yeah, why I'm asking this, because if we go to a metric of more or less 10 kilowatt hours per day, in a house, in an apartment, most of these cars, electric vehicles, electric cars, they have a battery between 40 to 100 kilowatt hours. Let's imagine, for instance, one of the premium ones with the battery pack of 100 kilowatt hours. 100 kilowatt hours that are really in our parking lot, in our garage. How many days we can actually power our home with that car? So if we have a consumption of 10 kilowatt hours with a car of 100 kilowatt hours, we can power actually for 10 days or even more our house. So if we are having issues of security of supply, or if you are having issues of quality in our power system, so power quality, that's really a case, and you have seen actually many cases like these big power outage or blackouts, for instance, in Texas, in California, in Greece, in the last years. That's actually quite a powerful tool that we can have in our house, and it's basically a big battery just on wheels. So yeah, that's basically, and we have seen actually that, for instance, some Nissan Leafs, they already come with the possibility to do a vehicle to load. The CHAdeMO standard, they also allow that. And if you look in the list of many cars, many of those, they are already kind of ready to do a vehicle to X. Of course, there are plenty of limitations in terms of regulation. We don't have, as you mentioned it, in those challenges, regulation, legislation. That's also a problem there. But yeah, the dream is that we can flatten the curve. You know it is very well. We have these peak consumptions usually in the evening and in the early morning. So if we can charge our cars during these valley hours at home or at work, and also overnight, we can get that power, that energy back to the system during these peak hours and really flatten the curve there, and that will be extremely good, especially with all of these new tariffs that we are getting in our electric system to maximize the efficiency of the system and also the utilization of our power in the country. Another part is we did some measurements actually on real onboard chargers. And this is, for instance, some of the ones that we have in the lab. We have a Texas Instrument one and an Infineon based one. And here I mentioned that most of these chargers work at the rated power of 11 kilowatts. More or less in this area, and we have tested the efficiency of those chargers at this power, relatively high, so to say. So that's not a problem. But what we are having today is, for instance, in Energyville, we have actually that very same example. We have more than 50 charging points, and we have more or less an installation of 100 kilowatts. So if you think 100 kilowatts divided more or less in 50 points, we have mainly 2 kilowatts of power. or we can derate the power. Sometimes we charge some cars, sometimes we charge some others, and that's the concept of a smart charging. I think you have seen also that in the electromobility courses, or and perhaps you will see it also in the more into the power systems. But we are doing what is one of the techniques to do a smart charging. But if we do is if we do a smart charging, for instance, using solar, as I already mentioned before starting this section, we have these converters inside these systems, and they are not optimized for light loads, as we saw in with this soft switching, hard switching part. And because of that, we are actually ending up in really low efficiency range parts. So imagine all of that energy that we are generating with solar panels, with windmills, even with nuclear power, with gas and so on. We are actually losing quite a lot, sometimes even 30, 20%, even in some cases, even way more, just because of these power conversion systems there. So that's one of the things why we should put also emphasis in the powertrain. We don't have a problem only in the infrastructure. We have also a problem inside the car. That's one of the messages from this session. Don't think that the cars are already perfect, because they are not. This is actually some measurements that we have done in the lab with the Tesla Model Y, new model actually. And there we have different powers, a different state of charges. Like for instance, here you can see state of charge between 16 and 36. That's the light line, and a state of charge between 92 to 95. So the last stage. You can refer to this one as relatively fast, and this one to relatively slow. Depending on the power, of course, and depending on the smart charging strategy. But what is important to tell here is these values. So 10%, 13%, and this is only after 4 kilowatts. So if we go really before 4 kilowatts, you can see that we will end up in really extremely low efficiency. But at least in this measurement, we didn't go before or below 4 kilowatts. So yeah, imagine all of that energy. That's something that I always try to emphasize, that all the energy that makes our cars move, electric cars, really need to go first through a power converter. Either if it's an onboard charger or an offboard charger, all the energy that we use goes through those components. And basically, we are wasting a lot of energy there, and we are not realizing. Of course, we are paying for that energy. We are generating quite a lot of CO2 there just because of these converters. And it's not like there is an alternative. Of course, we need those converters. So yeah, low state of charge efficiency we have there. So yeah, we have the challenge of bidirectionality, either charging or discharging the battery. We know that already. So we have the problem that these onboard chargers, they are not small. They're actually large. They are big. They are expensive. They are bulky. They are heavy. So in this power drive project that I was mentioning at the beginning, we have the objectives of increasing the power density, increasing the efficiency, making it cost effective, and making it bidirectional, so allowing power to X. And by the way, this is a real photo of one of the prototypes that we have in the lab. It's not, let's say, the final prototype is literally the first prototype, so it's not that compact. But yeah, there we are testing different approaches, and we will see in a minute. So one is the design. The other thing is how we use actually the onboard charger. And there we have, for instance, the challenge of involving, for instance, real charging algorithm, real data to see actually what will happen inside the onboard charger in terms of, for instance, losses. How to play really with the state of charge, how to play with the smart charging strategy in order to maximize efficiency. Here, I just want to mention several technologies. We call it this a research roadmap in this particular case of the onboard charger. We can have like the current state of the art is dedicated mainly for 400-volt battery packs. Sorry, we have really the need of wide frequency ranges as using conventional cooling strategies, not necessarily integrated. As I mentioned, one of the targets of this project is to integrate these onboard chargers, for instance, in batteries. And there we are, what we are doing in our group is to improve these onboard chargers using these mainly 6 technologies. So we are taking into account 800-volt battery packs. We are making quite an effort in the topic of magnetics, because transformers, if you ever visit, and it will be quite nice if you visit us and you see, because we open those onboard chargers and we look inside. The transformers are extremely large, are extremely bulky. Wide bandgap semiconductors, as I already mentioned, gallium nitride, silicon carbide. We are also checking the possibility to change voltages, so variable voltages, and how to work with that to do better cooling, and as I mentioned, to integrate these devices into other systems like batteries or motor and inverters. And yeah, that's one of the main activities right now, goes to the point of magnetics. Yeah, just to do a zoom in some of those, like for instance, 800-volt battery packs. It's a trend. So several premium cars like the Porsche Taycan, Lucid Air, the Porsche Taycan, Macan, sorry, they're using these 800-volt or higher voltages are also good because we can have faster charging. Again, because we are lowering the current at the same power, that's actually good, so less losses. But of course, that means that we need to redesign the onboard charger, and that's also important. Semiconductors. So wide bandgap devices are used because they offer low switching losses. They also can go really in high frequency operation. So conventionally, if we use conventional silicon, we could switch those in tens of kilohertz. But with silicon carbide and gallium nitride, we can go really in hundreds of kilohertz. You know it from your power electronics courses. I just see a question of Tiago, sorry, that doesn't exhaust the car battery a lot. What do you mean? You mean the 800-volt situation? Maybe if you open your mic, that will be easier, Tiago. The B2X. Uh-huh. That's something that I was saving it to next week if we see each other face to face to have this discussion, because indeed one of the concerns, so to say, if you look, for instance, in LinkedIn and in social media regarding this technology, is that many people tend to think that B2X is really bad for the battery, in terms that we are actually cycling more the battery and we are exhausting, yes, the battery more. Because of course, if you charge the battery to 100% state of charge, and then you use it at home to offer services, you end up in a lower state of charge, let's say 80%. So you sold 20% of your energy to the system, or you use it to something else. So yes, that's of course use the car, use the battery. I would not say that it exhausts the battery a lot, because something that many people don't take into consideration is the fact of power. When we use the battery, perhaps I will use one of the previous slides in a better way. Just give me 1 second. I will use. Yeah, this one. 21. when we use this one, we know that when we are discharging the battery, we have a motor of hundreds of kilowatts. So we are discharging the battery in a really fast way because we are moving the car. And sometimes if we go fast, if we drive at 120 kilometers an hour, of course, we are requiring quite a lot of power. So we are discharging the battery at really high rates, or really fast, so high power, hundreds of kilowatts. But when we are actually discharging the battery towards the house or towards the load or towards another car, we are actually using the onboard charger. And again, the onboard charger is limited to several kilowatts. And if we have seen actually real prototypes of vehicle 2X, those are really in the range of few kilowatts, 3.3 kilowatts. So that's even if we use 11 kilowatts, we are not discharging the battery really at a fast rate. We are discharging the battery really slow. So will that be harmful to the battery pack? Not in as we expected. Of course, we are using the battery, so that's it's not like it's nothing. Of course, we are using the battery, but we are not damaging the battery as many of us think, and that we would be basically as riding the car, because it's not. And something that many people don't know is that actually, even if we don't move the car, we are discharging the battery anyway, meaning that we are, for instance, there mainly in the Tesla cars, they have this Sentry mode. Basically, that is like a sentinel mode, where the car is actually all the time recording and all the time looking if someone passes by the car, starts recording, or even you can access data from your phone to the car. For instance, if a door was left open, or to check the state of charge of the battery. So the car is actually a computer that is always working. So the battery is actually discharging the whole time. So if you discharge it at 1 kilowatt an hour, or let's say 1 kilowatt hour every hour, or if you discharge it at 3 kilowatt hour every hour, it will not make a big difference, because that's happening already. So will that be a big impact to the lifetime? I don't think so. It's not like nothing, but it's not like many people think that it's actually extremely harmful for the battery, because it's not. It's really low power. Does it answer your question? Yeah, good. So let me get back to the slides. So yeah, we were talking about this when we try to really work at high frequencies. Magnetics become a bottleneck. Actually, you can see here the semiconductors, and here in between the transformer, large and bulky. So magnetics, many people think that they are a bottleneck because we cannot downsize electronics at the same rate as with semiconductors. And this is the case of the e-tron that I was mentioning. This segment in blue is almost 1/3 of the whole onboard charger. These are only transformers. And that's an inside. You can see here, for instance, capacitors. Inside there is plenty of capacitors, and all around is basically aluminum for cooling the onboard charger. So there we have magnetics, which are basically iron and copper, and we have capacitors, and we have cooling systems, so heat sinks. So basically, they're the so-called passive components. We have a lot of those. They are by far the most expensive, the most bulky, and the heaviest ones in this system. So it's quite important to put attention to those. There are 3 transformers there, because it's a 3-phase system. And what we are doing, and Hans is actually working on that, is how to go from a system with where we use all of this space and material to 3 transformers, to integrate those into a single one here. So we are saving 2/3 of the space of those transformers. We can have an improvement in size, cost, and CO2. We do that basically with analytical models. We do that with simulation, finite element analysis, and with innovative concepts like, for instance, new arrangements, new magnetic materials, new cores, new windings. Like, for instance, these are made with PCBs. So PCB windings, those are the things that we are doing in our group. And the final one is a converted topology. So we are playing with the topology, not only working, for instance, with dual active bridge or LLC converters or CLC, but checking what to do. And quite important to mention that we have put all of this information into this paper. So mostly sure we will put this paper to the evaluation of the course. So please have a look at this, and we can discuss it also next week, because many of you will need to read this for the exam at the end. So yeah, it's a paper about bidirectional onboard chargers. We did a quite nice review of those, checking really into a lot of these concepts that I have been mentioning here. So yeah, please download it and read it, and then we can discuss it also next week. And if not, yeah, some of you need to do the exam with this particular paper. In this paper, we do an analysis of quite a lot of onboard chargers from academia, from industry, from car makers. Like, for instance, you can see here Chevrolet, Renault, Tesla, and the green ones. And then you can see also more industry related, like tier one companies like Wolfspeed, Infineon, gallium nitride, GaN systems, and so on, and also some from academia. And here we have seen actually two trends. We are comparing basically power density versus efficiency, peak efficiency. We have seen two trends, like there are the so-called extremely dense onboard chargers, and that's what we called before this. We call single stage converters. If you're interested in this topic, we can discuss it next week in detail. What single stage mean, and all of these, the ones that are used nowadays, they are two-stage onboard chargers mainly. And yeah, here we are actually checking state-of-the-art designs, looking into the topologies, and we are also looking into the trends and opportunities, looking, for instance, into the opportunities for the markets, for academia, for industry, and so on and so on. If we do a zoom a little bit into this, we can check, for instance, the technologies there. Once again, like the semiconductor devices, magnetic components, cooling and packaging, power and voltage levels. Like if we talk, for instance, about 400, 800, or even 1200 volts today, what about power? If it's 3.3, 6.6, 11, 22 kilowatts. Even there is a case of a 43 kilowatt onboard charger made by Renault in France. Topologies and architecture, and the concept of integration. And there we have checked more than 500 papers, patents, and documents, and we put that basically in that paper. Yeah, we check, for instance, high power density that can be checked or can be obtained through different strategies. Like, for instance, this concept of a super integrated magnetic components, transformers and inductors, quite compact arrangements of topologies, super compact and flat inductors and transformers, and the concept, of course, of integration. So yeah, some of the points there. We do that looking into the trends, like what is the trend, for instance, in power density and switching frequency. Like for some of those, they are already switching at 500 kilohertz, for instance. That's quite high. and looking what is the trend there, and looking also into, for instance, research opportunities, for instance, for our groups, in Europe and around the world. Where are the efforts, like for instance, if it's in silicon GaN or silicon carbide, or if, for instance, if it's mainly in 400 volts, but today we are also talking about 800 volts. And as I mentioned, that starting this year and next year, we are also doing developments for 1200 volt powertrains in electric vehicles. And this is all together the topic of research of Hans Wouters, one of our researchers. He has been developing these onboard chargers for vehicle to X or bidirectional ones, 800 volt ones. And yeah, these are some of the achievements that we have got so far. If you're interested in this, just let us know. We have plenty of opportunities in terms of PhDs and master thesis and so on and so on. Work even as a researcher. It's a quite nice topic, and we are really investing a lot on that. Good. Before I jump into the last part, are there any questions regarding onboard chargers? So yeah, please read the paper, download it, and start reading it. And in the session next week, we will discuss it in detail if you have quite specific questions. So once again, we started really on the high level, looking what are those research topics that we have in Energyville, the importance of electromobility, and then the importance of battery charging into the powertrain. Now we went through the topic of onboard chargers, and I will finalize the session today looking into offboard chargers. And here the acknowledgement is to Dr. Camilo Suarez. He has worked with us during his PhD and now as a postdoc in the topic of offboard chargers, with quite an emphasis on magnetics. Good. I was mentioning a lot about modularity. If we look inside, this is a real Tesla onboard charger. This is actually how it looks like. Many modules, if you can see here, 2, 4, 6, 8, 10 modules. Usually these are like 250 kilowatts, depending on the technology of the Tesla supercharger. Even today, we have in the plans of Tesla to develop 800 kilowatt fast charging stations, and they will be deployed in the future. But the ones that we have today, like for instance in the vicinity of Leuven, there are plenty of, and Zaventem, there are plenty of Tesla superchargers. They look like this. So again, we have the AC source, we have a filter, and then we have all of these modules. And each module could be between 12.5 to 50 kilowatts, depending on the configuration. And they're basically done with this AC to DC segment, and then a DC to DC part. Why we use a DC to DC conversion if it's already DC is basically to have a galvanic isolation in between for safety purposes only. Some other advantages, like the possibility to isolate the two segments, possibilities to have higher voltage conversion ratios, but the main one is actually safety. So yeah, that's how it looks like. So each of these is basically a module. So I was mentioning that power per module can change depending on the intention or the purpose of the offboard charger. So if we have an station of relatively low power, we can have only few modules. If we have a larger station, like one of these Tesla superchargers, we saw that we have actually 10 modules, for instance. And there are plenty of commercial solutions. This list is a little bit outdated, like a couple of years outdated. Still, we are working on making it up to date, meaning today, 2024. But by 2022, 2023 it was quite updated. There were already several companies developing this hardware, like this PRE charge point in the US is one of the largest, EVBox, Tritium, Tesla, of course. There you can see a variety of companies, and there you can see voltages, powers per module, like for instance 25 kilowatts, 31.25. Here there was not reported, same. And for instance, in some of the Tesla superchargers, we found 11 kilowatt modules, between 11 kilowatt and 150 kilowatts. So yeah, you can see there the power per module changes between companies. So there is no unique truth, so to say, in terms of what is the good power per module, because of course that depends pretty much on the segment that you try to target in this regard. And most of them, they reported 95% at full rated power. Remember, that is one of the key takeaway messages from this class, is that we do not think, or we do not need to think always at rated power. We need to also to check what it happens at light loads in terms of efficiency. So I already mentioned this efficiency issue that we have with onboard chargers, and it's even more critical with offboard chargers. That's it's already there. So overall losses increase. So yeah, again, single versus modular. Why we have modular approaches in these systems is basically because we can have, if we have only, for instance, charging a Taycan at 350 kilowatt, a Porsche Taycan, we can use a single converter at 350 kilowatts. We will have problems of high currents, high voltages. We need, of course, really high voltage semiconductors. We will need a really high flux compact magnetic cores, and we will require also extremely high performance cooling systems. While, for instance, if we're using the modular design, we can have, for instance, two modules at 175 kilowatts. And that also gives us the opportunity to charge more than one car. So if we have these two, we can actually charge, for instance, two Audi e-trons, and there we can offer more flexibility, scalability, reliability is high, efficiency is higher at light loads, but it still is more complex. So we need a better control strategy. And here, for instance, we cannot charge the Audi e-tron. Of course, can be charged, but we don't use all the power that we can have at hand with this single converter. And yeah, there we can have different power modules, and there could be a different interconnection inside the cabinets. And also we can have this configurability. So if, for instance, one of the modules fail, we can still have the rest. For instance, if you have a single converter, if that converter fails, of course, that's the 100% of the station will fail. Well, in this case, we have certain redundancy in the system. And also the concept of power shading, so to say. So if we have, for instance, one module, usually the efficiency profile is like this. It goes up and then it goes down. So every converter has that. The point that it actually starts going down, we can activate another module, and therefore we can have still higher power and higher efficiency, and so on and so on. So we can have module 1 only at low power, module 1, 2, 1, 2, 3 at medium power, and all the modules available at high power. And therefore we can have more or less kind of like a flat efficiency profile. So that's the concept of power shading in these systems. Let me check the time, because still we have 30 minutes, but I would not like to use all the 2 hours. I have one video which is quite interesting, but I don't know if you will have audio. Can you confirm if you hear the video, please? I think even I cannot hear it. Yeah, but anyway, you can see it. The power module, and in this case of charge point. There could be, of course, a power block. As I mentioned, we can add more capacity if we have more modules. And we can power actually several charging points, several outlets, and increase the power of these ones. And of course, we can offer fast charging. They call it here ultra fast charging. So referring, for instance, to systems of 350 kilowatts and so on. Yeah. So yeah, that's basically the concept of modularity. Now, for instance, what happens if we think towards big fleets of vehicles? Do you hear it there? You hear the audio? Yeah, I will play it. Even if you don't hear it, at least you can see it. Yeah. So yeah, that's basically the concept. So there are some other points that we need to consider. For instance, when we go modular, and it's basically what could be the power per module that we can have in these systems. That's a big question. Like if it is, for instance, 30 or 25 or 20, how we can determine really the power per module. And some of the cases is, for instance, cost. So if we have, for instance, many modules, or someone would say, of course, we can offer more flexibility if we have extremely way many modules. Like if we have a charging station of 350 kilowatts, and we do 350 modules, so modules of 1 kilowatt. And the answer could be yes, why not? We can have extremely high redundancy in that case. But there you can see how this trend moves. Having modules of 1 kilowatt, 5 kilowatts, or 10 kilowatts is extremely expensive, while, for instance, going higher and higher in power reduces the cost per kilowatt of installed power. And there is a point where it starts, let's say, flattening the curve, and that's more or less the point that we select. This is, for instance, the case for instance, conventional silicon. If we, for instance, put into consideration silicon carbide, we could actually reduce that cost, and we can actually go for lower power. So in some cases, using certain technologies can also increase the number of modules, having different, for instance, targets of electric vehicles. We can actually change the power per module. Like, for instance, if we have a Tesla supercharger where most of the cars are actually Teslas, then we can use certain technology. If we have a technology or let's say a charger that is intended to be used in many of the vehicles out there, then we can change the power. So there are many factors that can affect the power per module. There are also the concept of multi-module configurations, like for instance, we can have single input, multiple outputs, and so on and so on. So we can have, this is purely into the power electronics, what kind of modules we can have there, how we interconnect that, if it's series or if it's parallel. That's also possible to evaluate, and it's also one of the open questions still to answer, depending on the conditions, what could be the best or the suitable technology. So most of the time we can use, for instance, input series, output parallel, and so on. We use actually these concepts a lot, using, for instance, the concept of solid state transformers. That's purely into the power electronics course, but we also bring it here to evaluate what happens if we increase, for instance, the frequency of certain transformers, and therefore we can downsize those, and that will be quite effective in the concept of electrical installations. So we will be talking a lot next week. But yeah, in a nutshell, we are using front-end converters, dual active bridge converters, the transformers, and then the rest in the other side, so inverters, and then back to the grid. And here in between, we can get use of power to charge electric vehicles. But yeah, we will discuss that during the next week. Just to finalize, same as I did in the onboard charger to the offboard charger, that was the topic of Camilo Suarez, one of our researchers. He was exploring all of the areas of charging between in voltage. This is the CCS standard, going from almost 950 volts to 200, from 0 to almost 500 amps. Those are all the points, and we were building actually modules of these silicon carbide onboard chargers, checking the efficiency and making it flat. Using concepts of magnetics, we call it a controllable magnetics, quite special, quite dedicated to these topics. Good, and with that, I would like to finish the talk today. So yeah, I am quite active in LinkedIn. We also have our YouTube channel with quite many presentations. We have one software for designing of power converters, looking, for instance, into data sheets. It's called Powertrains. So yeah, if you're interested in one of those, just let us know. So it's the time for the Q&A. We have several minutes, so it's up to you to use those. So feel free to open your mic or to type it in the chat, and then we can discuss it.
I have a question. Do we have this presentation on Toledo uploaded or not?
No, it's not uploaded yet, but I will upload it later today. Once we have the, I need to add the polls, the results of the polls to the slide set, and then it will be uploaded. Same as the video will be uploaded as well. So the recording, and you get the chance to rewatch it again. Yeah.
Okay, thank you.
Yep. Any other questions? Okay, if not, I will stop the recording here.